Why is BCI signal acquisition so difficult? Imagine trying to listen to a whisper across a noisy room. That's similar to what scientists face when capturing brain signals for brain-computer interfaces. The signals are incredibly faint, making them hard to detect clearly. These signals come from electrical activity in the brain, but they are often weaker than the background noise around us. To develop effective brain-computer interface applications, we need to pick up these signals accurately and reliably. Electroencephalography, or EEG, is a common way to do this without surgery. It uses small sensors placed on the scalp to record brain activity, but the signals have to pass through layers like the scalp, skull, and cerebrospinal fluid, which all distort and weaken them. This makes it tough to get a clear picture of what the brain is doing. The signals are also low in resolution, so it's hard to pinpoint exactly where in the brain they come from. That's a big challenge when trying to develop precise applications, like controlling a robotic arm or communication devices. Invasive electrodes, which are implanted inside the brain, can pick up stronger and more detailed signals. But they come with risks. The brain tissue can react negatively to the electrodes, causing inflammation or damage. The materials used for these electrodes often don't match the softness of brain tissue, which can lead to further problems over time. Researchers are working on making electrodes that are flexible and compatible with brain tissue to improve long-term stability and signal quality. Another big issue is that brain signals are not the same all the time. They change based on how a person feels, their level of attention, or even fatigue. This variability makes it difficult to get consistent signals for the same task. Plus, external noise from muscle movements or electrical interference from nearby devices can drown out the signals we want to record. To fix this, scientists use advanced filtering and signal processing algorithms, but these depend on the initial quality of the signals. If the signals are too weak or noisy, it's much harder to decode what the brain is trying to tell us. The process of figuring out exactly where in the brain the signals come from is called solving the inverse problem. It's a complex mathematical challenge because surface measurements don't directly tell us the location of neural activity. Combining different imaging techniques like functional magnetic resonance imaging or optical imaging can help, but these methods are costly and add complexity to the system. Finally, users need to learn how to control their brain activity in ways that the system can recognize. This training can take time and varies from person to person, which can slow down the development of practical applications. All these factors, weak signals, noise, biological and mechanical hurdles, variability, and user learning, make acquiring brain signals a tough task. Progress in electrode design, signal processing, and user training is ongoing. Improving these areas is key to making brain-computer interfaces more reliable, so they can someday help people control devices or communicate more easily.